The universe is a vast and mysterious place. For centuries, we have gazed up at the stars and wondered about the fundamental nature of reality. What are we made of? What are the rules that govern the cosmos? In the 20th century, a new theory emerged that revolutionized our understanding of the universe: quantum mechanics. Quantum mechanics is the study of the very small, the realm of atoms and subatomic particles. It is a world where the familiar laws of classical physics break down, replaced by a set of strange and counterintuitive rules. In the quantum world, particles can be in multiple states at once. They can tunnel through barriers and become entangled, their fates intertwined in ways that defy common sense. One of the most important concepts in quantum mechanics is uncertainty. At the subatomic level, it is impossible to know both the position and momentum of a particle with perfect accuracy. This is not due to limitations in our measuring instruments, but rather a fundamental property of nature. The more precisely we measure one quantity, the less we can know about the other. This inherent uncertainty has profound implications for our understanding of the universe. It suggests that at the most fundamental level, reality is not deterministic but rather probabilistic. The future is not predetermined but rather a tapestry of possibilities, each with its own likelihood of occurring. One of the most mind-boggling concepts in quantum mechanics is wave-particle duality. This principle states that particles such as electrons and photons can exhibit both wave-like and particle-like behavior. This dual nature has been confirmed by countless experiments, leaving scientists baffled and intrigued in equal measure. Imagine a beam of light shining through a narrow slit. Classical physics predicts that the light will pass through the slit and create a single bright spot on a screen behind it. However, in the quantum world, something much stranger occurs. Instead of a single spot, the light spreads out and creates an interference pattern, as if it were a wave passing through the slit. But here's the twist. If we send individual photons one at a time through the slit, we still observe the same interference pattern. This implies that each photon interferes with itself, acting as both a wave and a particle simultaneously. It is as if the photon travels through both slits at once, even though it is a single entity. Wave-particle duality challenges our classical intuition about the nature of reality. It tells us that objects we perceive as particles can also behave like waves, blurring the line between these two fundamental concepts. The implications of this duality extend far beyond the laboratory, influencing our understanding of everything from the behavior of light to the structure of matter itself. Quantum mechanics represents a radical departure from classical physics, the physics of everyday experience. Classical physics, developed by giants like Isaac Newton, describes the motion of macroscopic objects with remarkable accuracy. It governs the trajectories of planets, the swing of a pendulum, and the flow of fluids. In the classical world, objects have definite positions and momenta, and their future behavior can be predicted with certainty. Quantum mechanics, on the other hand, deals with the realm of atoms and subatomic particles where the rules of classical physics no longer apply. In the quantum world, particles do not have well-defined trajectories. Instead, they exist in a haze of probability, their positions and momenta smeared out like blurry patches of paint. Another key difference lies in the nature of energy. Classical physics treats energy as a continuous quantity, like a smooth ramp. Quantum mechanics, however, reveals that energy is quantized, meaning it can only exist in discrete packets, like steps on a staircase. This quantization of energy has profound implications for the behavior of atoms and the emission and absorption of light. One of the most bizarre and intriguing phenomena in quantum mechanics is entanglement. When two particles become entangled, their fates become intertwined, no matter how far apart they may be. Measuring the state of one particle instantly determines the state of the other, even if they are separated by vast distances. Imagine two coins flipped simultaneously, one landing on heads and the other on tails. In the classical world, this is a random event, with no correlation between the two coins. However, in the quantum world it is possible to entangle two particles such as photons in such a way that their properties are correlated. If we measure the polarization of one entangled photon and find it to be horizontally polarized, we instantly know that the other photon, no matter how far away, must be vertically polarized. This instantaneous correlation, dubbed spooky action at a distance by Albert Einstein, has been experimentally confirmed time and again. Entanglement has profound implications for our understanding of the nature of reality and the limits of locality. It suggests that there are connections between particles that transcend space and time, challenging our classical notions of cause and effect.